Okay. All right, so ready? All right, so today we're going to continue on a bit with integrating vector fields, learning a little more about vector fields and line integrals. And then on Thursday, we'll get started on surface integrals. Well, maybe not surface integrals. We'll do Green's theorem, which is a prelude to that. So for the exam, the third exam, I have posted those last night, those scores last night. Average was, I think, 63, which is, I think, pretty normal for this stage in the game. If you struggled, I noticed during some of the grading that it seemed like some people were struggling with some of the more basic ones. So if you've got, like, I would say problem one, if you struggle with problem one, or if you struggle with some of the basic integrals, I would try to spend a little time reviewing those before the final. But people did all right, and it was a really well spread out score. It seemed like the class is pretty much all over. So we've got some really strong students, 200%, and we've got well, some people are struggling a little, but it's never too late, except when it is. Okay, so I do want to make one correction. There was nothing wrong with the formulas that were written down last time, but I said something that was not correct. So when computing this flux integral, we have this form where we just basically, if we parametrize our curve according to the orientation of the curve, you get this formula that we derived last time, where the parametrization R of t is from A to B. And the formula was correct that I wrote, which was just you take your velocity vector and you sort of switch the x and y and put a negative in front of the x. But I said this was a counterclockwise rotation. This is actually a clockwise rotation of the tangent vector in the plane. So that was a mistake. I'm sorry about that. Just wanted to clear that up. All right. So, and another thing that we didn't quite get through last week, which we should have, and you should have some exposure to, is this sort of differential form of vector line integrals. So it's really just an alternative notation at this level. It's not anything to worry about. It's not a new concept, really. And sometimes I would say it's sort of easier, more natural to use this notation. You'll see it in applications for sure. But so let's go over it. So let's say we have a vector field F, and we have our components P, Q, and R. There is in the text and in my notes sort of a overuse of P and Q and R. Sometimes I use it for points and sometimes for functions. In this case, these are functions of X, Y, and Z. So this is a vector field. Then sometimes this differential form, sometimes you'll write, rather than writing the form or the vector line integral like this, there's an alternative way of writing it, which is just you write P dx plus Q dy plus R dz. The idea is you're dotting F with the velocity. And so you can kind of think of dx, dy, dz as a velocity of a parametrization along the curve. So let's do a problem just using this notation so that it's not totally unfamiliar. All right, so let's calculate the vector line integral. Say integral over a curve C, and this curve will mention what it is in a moment, of negative y dx plus x dy. So this will be, the differential form I'm writing up here is for three-dimensional vector field and a curve in 3 dimensions, but we'll do this in 2 dimensions. And so this will be over the curve, the circle of radius, I don't know, let's say 3, centered at the origin. And we need one more ingredient when we're doing vector line integrals, and that's an orientation. So I'll say going counterclockwise, so moving counterclockwise. All right. Well, you do the same, you need the same information that you need for the ordinary form that we have. In particular, the most important thing you'll need to make a computation in this case is a parametrization of your curve. So we'll parametrize, well, we're dealing with a circle centered at the origin. We know how to parametrize that. So we'll say that R of t equal 3 times cosine of t, 3 times sine of t, from t from 0 to 2 pi. So incidentally, I want to ask everybody here, what if I had instead said clockwise here rather than counterclockwise? What should I do in my first step? Negative? Put a negative here, or negative on both, or on the 3 sign? Okay. Is that the answer? Negative on 2 pi. That's a little harder to do. I mean, if you go from negative 2 pi to 0, you could put 2 pi minus t, I guess. That might do it. So you're right. You can do, certainly this is a possibility if you were to do clockwise, but there are actually a lot of possibilities. You could do this too, right? You could switch the sine and the cosine, right? The point is that especially when you're parametrizing a closed curve, namely a curve that doesn't have a start and an end where you could put, there's a lot of different possibilities. And so, but that is one. Putting 1 negative, and there would be fine. If you did 2 negatives, you would have trouble. You would have not done that. Okay, good. All right, so now we've got a parametrization, and now what you do is I find it helpful just to say, okay, well, this is equal to, this parametrization we found is equal to, say, x of t, y of t. And now the idea is we've got these 2 functions for x and y, and we've got a bunch of x's and y in here, and we can just put these in, okay? So then we'll have that this integral from c minus y dx plus x dy is equal to the integral. We'll use our bounds of integration, our bounds for the parametrization, I should say. And I've got a negative y, so that's -3 sine of t, dx, and I'll write it out, d of 3 times cosine of t, plus x, which is 3 cosine of t, times dy, which is 3 sine of t. And then I've got a dt here. Well, I don't have a dt, I'm sorry, and these dt's will come out of this expression here. So here let's continue. So d of 3 cosine of t is 3 of sine, as -3 sine of t times dt. So I'll get a 9. Jeez, Pete's, sorry guys. 9 sine squared t dt here. And similarly, d of 3 sine of t is 3 cosine of t dt. So I'll get 9 cosine squared t dt. And then, okay, I've got 9 sine squared plus 9 cosine squared, that's 9. So I just get the integral from 0 to 2 pi of 9 dt, which is just going to be 18 pi. Okay. As I said, this is not anything new. It's not a new quantity or new concept. It's just new notation. And if you kind of look at it and compare it to what we did before, it's really the same thing. But you'll see this notation frequently. Okay. So now I want to recall what we were, where we sort of left off last time. So we left off with this notion of a generalized Stokes theorem. And I talked about how we were going to see this theorem in many different forms for the remainder of the course. And that's indeed the case. We'll see one today. So this is the format, or this is an actual mathematical formula, which is you'll read about when you go to grad school. I can hope, right? But it is even if this looks kind of wildly abstract to you, the point is that it summarizes the form of all of the theorems that we're going to write down. So having an understanding of this, or at least of the structure of it, will help you sort out the other theorems as we go. Okay, so the case we talked about last time, the example we saw last time, was sort of an example where you took an interval, say AB, and we took D was the derivative. Maybe we'll use X. Do an X. I don't know, I'll probably do T here. T dt, and we get this fundamental theorem of calculus. I'm just curious, I want to take like a little poll. How many people know what the fundamental theorem of algebra is? I mean, you guys all know the fundamental theorem of calculus. By a raise of hands. No. I guess that makes sense. I mean, it came later than the fundamental theorem of calculus. It's a much harder theorem. That's okay. All right, just curious. All right, so how about the fundamental theorem of arithmetic? How many know the fundamental theorem of arithmetic? It's just the name. I think you guys know this. It's the name. All right. Okay. So back to calculus. So today, what we want to do is we want to look at conservative vector fields. So let me recall, what is a conservative vector field? So we say F is conservative, and it doesn't matter what dimension we're in. It could be in 2, 3, n dimensions, 1 dimension. It's a conservative vector field. If F is equal to the gradient of some scalar function V, or some scalar function V. Okay. Good. So why are these so important? Well, for these vector fields, we have a theorem. It's called the fundamental theorem for line integrals. And it's written up there, but I'll rewrite it here and we'll explain it. It says the following thing. So it says if F is conservative with potential V, so remember this phi here in this equation is called the potential for F, or a potential. It's not necessarily constant or unique. It differs by a constant to other potentials, at least on connected domains. And C is a curve. It's a curve oriented from P to Q. In the domain of F. Of course, that's an important thing. We need it to be well defined on the curve. Then we have the following equation. Namely that if we take the vector line integral of this vector field F along our curve C, then this is equal to V of Q minus V of P. That's the theorem. So parenthetically, and this is sort of less rigorously, or at least we can write this as the following formula. Which is this is in line with this sort of general Stokes formula. Here in this theorem for conservative, or for line integrals, our gradient is the D, is our derivative. Our domain is a curve, an oriented curve, the boundary at 2 points. And the eta, this integrand, is going to be a function, a scalar valued function. Okay. So you may look at this and say, this is a lot of nonsense. Why do I care? I don't. And, what's the good of this? Well, let's do a problem. Let's see. All right. So let's see be the oriented curve. Parameterized. So if I say a curve is oriented, and then I say it's parameterized by a given parametrization, then I'm going to use that parametrization as the orientation. So it should be compatibly oriented with this parametrization. So parametrized by the following function, r of t equal the integral t of t e to the 1 minus t squared, hyperbolic sine, square root of t, times sine, ordinary sine, cubed, of course, by t, t to the 40th. Your usual ordinary curve from t equaling 0 to 1. And let's take f to equal xyz. It's our vector field. It's radially pointing outward. Compute the vector line integral. So how are you guys feeling? Down. I've got a thumbs down. Up. I see someone with a thumbs down. Okay, good. Yeah, I graded some of these exams. I know how you're feeling. Felt the same way. I think if you see this, you know, there will be like people will be pulling fire alarms. It'll be bad news. I get it. I don't like the look of this, and I wrote it. So this looks awful. If you were to actually, you know, take, I mean, just the first step. The first step in this computation, you have to take the derivative of r, find the velocity, and that step already looks awful. I've got this sinh, which I have to look up because I've forgotten everything. I have sine cubed, which doesn't look fun. I've got t to the 40th, which looks less fun. It's not too bad, but there's just a lot of ugliness. And then when I put all of this in to x, y, and z and take the dot product with whatever I get, it's going to be really messy. It's going to be really messy. I don't want to do that. So what I do instead is I take a look at my vector field. Let's not start here. Let's start here. And I ask this vector field, are you conservative? All right, I will not say things. What do you guys think? Is this vector field conservative? Maybe, maybe. I can't say it's wrong. How many think it's conservative? Yeah, good. You should, yeah, I mean, we're doing okay. If it wasn't, then it would be bad news. Okay, so yes, it's conservative. It's conservative. How many people could find a potential for it? Remember, you're looking for a function whose gradient is this vector field. What do you think? You want the first partial with respect to x to equal x, with respect to y to equal y, with respect to z to equal z. What's the antiderivative of x? X squared over 2. What about that of y? Y squared over 2. What if I just try this? Does it work? There's formal ways of going about trying to derive a potential. And I don't want to spend, you know, half hour going through this methodical way. I've done it in previous classes. It only got me hate email. Come to office hours. I mean, I'll go over it with you. I don't want to deprive you of this, but you can often look at these vector fields that are given to you and intuit what the potential is by just taking integrals of one or two components and feeling around. If you'd like the general method up, we can talk about it. It is in the book too. So here we do see that we get a potential. This is a potential. For F. And we can look back and say, well, wait a minute. That means F is conservative. I'm taking a vector line integral of this vector field that's conservative. It's just equal to the difference of this potential at the endpoints, my curve. What are the endpoints of this curve? Well, t goes from 0 to 1, so we just have to see what happens when t is 0 and what happens when t is 1. So P is the first point, R of 0. Okay, 0 times something, that's 0. Here I'm looking at this formula. And I'm putting in 0 for t. Sinh of 0 is 0. It's e to the 0 minus e to the negative 0. So it's e to the 0 minus e to the 0. That's 0. And who cares? Sine of 0 is 0. T 0 to the 40th is also 0. That's not too hard. Q, what happens when t is 1? Well, 1 times e to the 1 minus 1 is 1. And again, sine of pi, that's 0. So everything is 0 there. 1 to the 40th, still 1. Okay. What's 2 divided by 2? It's 1. 1 minus 0. Ah, 1. That's using this form. Okay. A lot easier, huh? Okay. So, I mean, it's a form of the fundamental theorem of calculus. So it's built to make computations much easier. Okay. So if you don't know it, then you're going to spend your life, taking derivatives of this nonsense and dot producting with this nonsense. And it will be awful, and you'll probably get the wrong answer because there's just a lot more likelihood of mistakes. So this is almost a miracle, right? Almost. So why does it work? Why does it work? Well, in fact, the reason it works is that it's really just the fundamental theorem of calculus. So if you look at this, along with one other thing, if I look at this f dot ds, and let's say we have this parametrization, I go from a to b of f of r t dot r prime of t dt. Now, this is impossible to work with, but if f is conservative, in other words, if we have a potential here, nabla v, then we can recognize something about this expression that maybe we didn't see before. Namely that this expression, if you look back in your notes or in the book, is an expression you've seen before involving the chain rule. Namely, this is the expression you would get if you composed v with r of t and took the derivative. So this is very temperamental. This is just the integral from a to b of v of r of t taking the derivative. dt. And now you have the fundamental theorem of calculus, because it's just an ordinary one variable integral. That's v of r, v minus v of r. Okay. So it's nothing really new, but except maybe the use of the chain rule in many variables. So that's the why. That's why. It's a miracle, but it's a miracle because the fundamental theorem of calculus is a miracle. But how do we interpret something like this? How do we interpret it? Well, it's actually telling us something quite interesting, really, which is that if we have some kind of vector field, or we have some conservative vector field, this. So let's say we have this vector field as f, and we say it's conservative. And we have some point P here, and we have another point Q here. Then what it's saying is that if I take a curve like this and sort of calculate the work that it takes to go along this curve relative to this vector field, then it will be the same amount as if I went, along some other crazy path. Because if you look at this formula, let me bring it down. If we look at this formula doesn't depend on C, the right-hand side. It depends on the endpoints of C. But whatever C you take here, as long as you're going from P to Q, you'll get the same integral, you'll get the same value. That's why that computation that we just looked at was so easy once we used this theorem, and why you could imagine if you put in some very insane curve, you would get a very hard computation on this side with the same easy answer over here. But this is essentially, I don't know, this is a sort of a conservation of energy type of statement, saying, no matter how you go from one point to another, it's going to take the same amount of energy, regardless of the path you take. This is where the word conservative vector field comes from. Mathematicians call this feature path independence. So we say vector field is path independent. Vector field, let's call it F. If whenever I take one of these vector line integrals, this only depends on the endpoints. In other words, I can vary any other part, I can vary the path and I'll get the same value, as long as I fix those endpoints. And then there's a theorem, which I won't go into details on in the book, but it's an important theorem, which says that path independence is the same thing as conservative vector field. Certainly one way we just showed that if it's conservative, it is path independent, but the other way is also true. This is sort of the same set of vector fields. Okay. This also tells us another thing about conservative vector fields, which is what happens when we take an integral of a conservative vector field over a closed curve. So let's say C is a closed curve. What does that mean? That means no endpoints. So it could be, just some kind of circle. I mean, it could be, if you're in, higher dimensions, you could imagine some kind of a knot tied up. I don't know. Something that has no beginning and end. It can also be disconnected. You could have, a circle, and you could have a, well, here, let me do that, do it a little better. You could have like, a link, two circles sort of linked up. So a closed curve just means there's that for any piece of it, it doesn't have a start and an end. So let's suppose we have a closed curve. There's actually different notation. It's not math. Actually, I don't think mathematicians really use this, but physicists certainly do. And I think applications, they use it a lot, which is if you have a closed curve and you're looking at the vector line integral, well, maybe mathematicians do. I just don't know the mathematicians that use this. I don't see it. They just write this way, just to sort of emphasize that this curve is actually closed. So if you see that notation, that's what it means. So suppose C is a closed curve and F is conservative. Then what? Well, then let's take a look. What can you guys say or tell me about this integral? Zero. This will be zero, right? So if you have multiple connected components and you're trying to compute an integral, you just you take each component, you take the integral on that, and you add everything up. Okay, so let's just say we have one closed curve, one connected closed curve. Then this is going to equal, we'll parametrize it somehow, so it's compatible with the orientation. But however we parametrize it, wherever we start, we have to come back to it. Our start and our ending point for our parametrization is the same point. So we're going to get, we'll have this theorem, VQ minus VP, but P is going to equal Q. So this is going to equal 0. So if you're doing integrals over closed curves and you see a lot of zeros, no matter what kind of closed curve you have, you should suspect, I probably have a conservative vector field. Not necessary, but kind of necessary. It will depend. Let me just give an example. So let's say, now I'm going to ask a question here, which is related to all of these concepts. So one thing we ran into when we had this problem just a second ago was we refocused our energy on the vector field itself rather than on the path or on the curve. And what we wanted to see right away is whether or not we had a conservative vector field. And what I didn't do there, we just kind of eyed it out. But one thing you certainly can do if you just want to test right away to say, okay, hopefully this is conservative, is you have this cross partials test. So let's look in 2 dimensions. And recall that the cross partial test here was the following. It's that if I take the derivative P with respect to Y, this should equal, maybe I should really not use P and Q here because I've got way too many P's and Q's. Let me call this something else. Let me call it G and H or something. I'm sorry, this is not going to, but I don't want to confuse this with the P's and Q's. So del G del Y is equal to, or del H del Y is equal to del G del Y is equal to del H del X. This is the cross partial condition. Just says that if this were conservative, then we would indeed have that this is equal to the derivative. This is equal to the derivative of v with respect to x, and this is the derivative of v with respect to y, if conservative. And then you could take second derivatives, and they should be equal. The mixed partials. So one might ask, how good is this test? If it's conservative and we get a negative, if we see that this is not equal, then, if it's conservative, we know it's equal. So in particular, what we can do is check this, and if it's not equal, then we know it's not conservative. But what if we check this and we get equality? Do we know it's conservative? Is it a perfect test? Will it just tell us, okay, we are in this case of conservative vector fields? So let's take a look at an example and see. Suppose we have the following function. If y over x squared plus y squared, x over x squared plus y squared. Let's apply the cross partials and see what we get. So we need to take the derivative of the first of the x component with respect to y. Okay, well, I'll get a negative 1 over x squared plus y squared. And then I get a plus, because I've got the negative here, x squared plus y squared squared. Right? I've got a 2y squared. Okay. Tell me if I'm making a mistake here. So I get a negative, I'm going to make common denominator, x squared plus y squared over plus 2y squared over x squared plus y squared squared, which will give me y squared minus x squared over x squared plus y squared squared. Okay, that's del y. Let's take del x over x squared plus y squared. Similar computation. Get 1 over x squared plus y squared minus 2x squared over x squared plus y squared. This is quantity squared. Again, make common denominator, x squared plus y squared squared. Here I have an x squared plus y squared minus 2x squared. So I get a y squared, I get a y squared minus x squared over x squared plus y squared squared. So they're equal. So the cross partial condition is a success. So can I conclude that it's conservative? That's the question. Let me draw a graph here. I'll tell you some things I know. If I take a circle out here, like that circle, oriented either way, and I take the integral of this vector field F that we're looking at along that circle, I'll get 0 for sure. If I take that circle over here and do the same thing, I'll get 0. If I take a curve just like this, and I integrate over that curve, I'll get 0. Vector field. It's interesting. It seems to me like this vector field, at least from all this evidence, shows all the symptoms of being a conservative vector field. But then I can do one thing. Let's take another curve. Let's take another curve. Let's just take our favorite curve in the world that's closed, say the unit circle. I don't know if it's your favorite, but okay. Let's take the unit circle. And let's compute the closed integral of our vector field F. Sorry guys, I'm moving this around a lot, but let me bring it down over this circle. So let's compute. Won't be a long computation. And we'll just orient the unit circle here counterclockwise. So this will be our circle C. Unit circle. Okay. Well, we're on the unit circle. So we can parametrize using, let's parametrize using our cosine sine. Our velocity vector is going to be minus sine t cosine of t. We know x squared plus y squared is 1 on the unit circle. So that simplifies this vector field F. And we just get the integral of F dot ds. This is the integral from 0 to 2 pi of, again, x squared plus y squared is 1, so we get minus sine of t, that's our y, cosine of t, dot minus sine of t, cosine of t, that's our velocity, dt. So again, we'll get sine squared plus cosine squared. That's 1. We're integrating from 0 to 2 pi. We get 2 pi. And I don't know a lot about 2 pi, but I know it's not 0. Right? So what we see here with this long, exhausting computation is we see that actually we've shown using this fundamental theorem of line integrals that if we have a conservative vector field and we integrate it along any closed curve, we should get 0. And we just integrated this vector field along a closed curve and we did not get 0. So this is not a conservative vector field, even though it has a lot of symptoms of being so. It's a very interesting vector field. We'll run into it again later. All right. See you Thursday.